This is Mr. Beck Does Your Homework. This is AP Physics, Homework 12.1. This is the introduction. And this homework covers Snell's law and critical angle, both of which deal with the phenomenon of refraction. Refraction occurs when a wave moves from one medium to another. So we're going to move from this medium up here into this medium here, and this is representing my wave. When that wave hits the surface, this side of the wave hits before that side of the wave, so this side of the wave slows down before that side of the wave, which means that there's a tendency to turn from this side to this side. So this wave is going to continue on in an angle different than the one it came in at. Depending upon how quick light moves in this substance versus this substance will determine how much that wave turns. And in order to measure how far the wave turns, we have to deal with angles. So we're always going to measure from a perpendicular line to the surface, and we're going to call this the angle of incidence. So I'm going to call that theta 1, and this is going to be the angle of refraction, which will be theta 2. So I have an angle of incidence and an angle of refraction. And if I'm going from somewhere where it's moving quicker to moving slower, then it's always going to bend towards the normal, this normal perpendicular line. So this, instead of going straight through, is going to bend this way when it slows down. Now how much it bends depends on how much it speeds up or slows down. So there's some phenomenon about this area and some phenomenon about this area that can be defined. And what we define that as is the index of refraction. We use the letter n for index of refraction, and the index of refraction n is going to equal c divided by v, where c is the speed of light in a vacuum and v is the speed of light in the substance, so it's just a ratio. So you will be given the index of refraction, or you'll be given the means to calculate it. So we have an angle of incidence, we have an angle of refraction, and we have an index of refraction for each area. So we're going to have an n1 over here and an n2 over there. Now Snell's law is how we calculate the angle of, how we relate the indices of refraction and the angles of refraction. Snell's law tells us that the index of refraction of the first substance times the sine of the angle of incidence is going to equal the index of refraction of the second substance times the sine of the angle of refraction. So that's n1 sine theta 1 equals n2 sine theta 2. So here's n1, here's theta 1, here's n2, here's theta 2. The biggest mistakes we make in this situation is switching the thetas or switching the n's. So you'll read a problem and you'll just throw whatever angle you hear first over here when maybe they're talking about what angle's over here. So listen for the words, is incident upon, which will give you this, or listen for the words is refracted at, which will give you this. So you'll be able to know, enters and leaves, so you're going to have a theta 1 and a theta 2, so between the two substances. So if I'm going from an area where it's quicker to an area where it's slower, then I have my angle of incidence, I have my smaller angle of refraction. And now, no matter what I do with my angle of incidence, if I change my angle bigger, well, this will also get bigger, just not so much. So still, this angle up top will be bigger than this angle at the bottom. If I take this and bring it even further, well, then this one will come out further, but still my angle at the top will be greater than my angle at the bottom. Now, if I do something interesting here, I can do it the other way. So let me take this and come in this way, and this and come out that way. So now, I'm going to take my angle of incidence. If I'm coming in nearly straight, then you'll see it'll come out nearly straight. And actually, going from heavy to light, going from slower to faster, it bends away from the normal. So this angle will be smaller than that angle. Now, if I change my angle of incidence so that this one's even bigger, then this one is going to bend, but it's going to bend even further away from the normal, okay? So this one will come in at another angle, this one will bend even further away from the normal. And if you see what's happening here, there's going to be some angle at which this one will want to refract right there along the edge. So I'll have an angle that is an angle of incidence over here, but my angle of refraction would be 90 degrees. This doesn't really happen. Instead of refracting, what happens is This surface right here will look reflective. It'll look like a mirror. So what'll happen is you'll wind up with all of the light reflecting instead. So we're going to get back to the law of reflection, where the angle of incidence equals the angle of reflection, and nothing will refract. This phenomenon is called total internal reflection, and it also has to do with the critical angle. This angle would be the critical angle, where at that angle it would seem to refract at 90 degrees. So to determine the critical angle for total internal reflection, we have to go back to Snell's law that says n1 sine theta 1 equals n2 times the sine of theta 2. But as we saw earlier, we had our surface, we had our light coming this way, and then refracting at some angle this way. So here's theta 1 and here's theta 2. But now this becomes n1 and this becomes n2, because this on the bottom is where I'm starting and this is where I'm ending up. So that means that this is going to be theta 1 and this is going to be theta 2. That's a 2. So n1 sine theta 1 equals n2 sine theta 2. I want to find out what theta 1 will give me an angle theta 2 that's 90 degrees at which it would reflect instead of refract. So I want to find the critical angle is what it's called. So I can say that n1 times the sine of the critical angle equals n2 times the sine of 90 degrees. Now what is the sine of 90 degrees? It's 1. So I can say that n1 times the sine of the critical angle equals n2. So that tells me that the sine of the critical angle is going to be n2 divided by n1. Now, if this is the sine of the angle, you know that you're going to have to do an inverse sine in order to get theta critical, in order to get the critical angle. So if you're doing an inverse sine of something, n2 over n1, well, if n2 is bigger than n1, you're going to get a domain error. So there is no critical angle when n2 is greater than n1, because then it would be going from faster to slower, and then you'd never get a critical angle because it would always refract. But if you're going from slower to faster, then it can bend more and more and more. So theta 2 will be greater than theta 1 if n2 is greater than n1. If n1 is greater than n2, then I can get a critical angle. So this only works if n1 is greater than n2, meaning it's speeding up instead of slowing down. So if n1 is greater than n2, then I have myself a critical angle. So you got to look for that, and you got to remember n1 is where it starts, n2 is where it finishes. Some of the problems in this problem set have, they'll tell you the substance, and they'll talk about the light going into the substance, and then they'll talk about the light coming out. Well, on the way in, you have n1 and n2. On the way out, now this is n1 and this is n2, so you have to be careful about that.